Dear students, this is Dr. Biju Vasudevan, Assistant Professor at Department of General Studies, Jubail University College. We are here for discussing the course Methods of Applied Mathematics 315. I would like to deliver all the courses through my video lectures online. You can find the links on your blackboard, and of course you can access to my YouTube videos. All these videos will be available in the YouTube channel, and we will discuss Math 315 for this semester. And remember, the syllabus and all the required documents of this syllabus regarding this course will be available on your blackboard. You should access, you should be very often visiting the blackboard. Of course, I am uploading the videos on regular basis. I mean regular stream basis, not summer stream basis. It's in the week 1 for regular basis. So week 1 and 2 regular basis will become week 1 for summer classes. So there will be videos for 15 regular stream weeks. So you can collect them for your summer courses. First 7 week syllabus will be for your midterm, the rest for the second half. Fine. In this video, we are going to discuss the introduction to Laplace transform, definition of Laplace transform, and if you have what is a transform? If you have two numbers, if I give in Roman numericals like 6 and 14, and we ask you to multiply these two. 6 multiply these two, so what will be the answer? So first you can transform this number into Arabic numerals. 6 and it is 14. Now multiply this one, you'll get 84. And now you can convert this into again Roman numerals L triple X and 4. This will be 84 in Roman numerals. So transformation is useful when it is very hard to solve the problem in its original form. There are many integral transforms. Generally, for a function f of t, where t is a time parameter and t greater than 0, the general integral transform can be defined as an improper integral from 0 to infinity k of s comma t f of t dt. This is a general form of an integral transform, and this k, this is the given function f of t given. So this k is called the kernel of the transform, kernel of the transform, right? And if k is considered to be, if k of s comma t, a function of s and t, is e raised to minus st, this integral transform will be called a Laplace transform, right? So so the function k is the function of s and t. What is s and what is t? Actually, we are going to see the definition right now. So the Laplace f is a function and time domain. The Laplace transform of the function f of t is integral 0 to infinity e raised to, this is clearly right, e raised to minus st f of t dt, integral from 0 to infinity, right? So it will be a Laplace transform provided the integral converges. If this integral converges, we will find its Laplace transform. What is actually happening here is you are converting a function from its time domain to frequency domain. Here the function will be a function of variable t, time domain. Here the output of the Laplace transform will be a function of s in the frequency domain. In engineering we can call it. So here f of t can be transformed to capital F of s. So different notations have been given. If it is f of t, it will be capital F of s. G of t, then Laplace transform will be capital G of s. If it is y of t, the Laplace transform will be capital Y of s. capital H of t is considered here, then it will be small h of s. That's it. Some different notations of the transforms have been given here. Why many engineering problems, the differential equations appear in time variable t as a independent variable, and the dependent variable will be y. In such differential equation, when we use Laplace transform, we can convert the differential equation into an algebraic equation and then solve it algebraically, and then bring back it to the original form from as by using inverse of the Laplace transform. That's coming up. Okay, that is the purpose of Laplace transform. We need to study Laplace transform for this course only to solve differential equations. So we will study how to solve differential equation by using Laplace transform in coming chapters. Okay. Some basic rules. We will derive all these rules using the basic definition. Before going through these rules, let's see some more. Okay. Before going through these results, let's have some more discussion on this. So exponential order. A function f is said to be exponential order for some constant c n m and time t is greater than 0. This value, the absolute value of the function m, should be less than or equal to m times e raised to ct for all t beyond t. See, all t, small t greater than t. So an example has been given here. See, an example has been given next function. See, f of t is equal to t square. We have taken the function f of t is t square. Here we can consider t is 0. T is 0 is the benchmark. Then for any t greater than 0, the function here, this is the function. This is e raised to 3t. This is t square, isn't it? Now we can, from the graph, you can find that t square is less than e raised to 3t, where c and m have been designed. So f of t, absolute value of f of t is less than, see, go back and check the definition, less than or equal to m times e raised to ct. C and m can be any constants, isn't it? So we have fixed it to 1 and 3. So this is 1 and e raised to 3t will be always greater than or equal to t square in this condition. From the graph we will find it. So t square is the f of t is t square is an example of the function which is exponential order, which is called exponential order. So for this function we can find a Laplace transform. The function of the condition why we study here exponential order. So it is a sufficient condition for existence of Laplace transform. If of x is piecewise continuous in the interval left to close and right to open 0 to positive infinity and exponential order, then the Laplace of the function exists for any s greater than c. C is the choice here, right? Okay. And now a counter example has also been given here. E raised to t square, we can check it is not always greater than e raised to ct, isn't it? It's not less than e raised to ct. The condition has failed. Okay, so we does not find a exponential order here. So for this term, for this function, there is no Laplace transform. Actually, in this chapter we don't need to verify this condition because all the problems that are given to us are piecewise continuous in the given interval and have exponential order. So we don't need to verify them. This is for your understanding. So this is the first thing we have to do. We have to solve these problems by using the fundamental definition of Laplace transform. What is the fundamental definition? The Laplace transform of f of t, integral 0 to positive infinity e raised to minus st f of t and dt. This is it. Here f of t, the given function will be replaced here, and we have to do this. So if you know how to use the basic formula, we can derive all the formulas. Let's just try the first one. There are 3 problems here. Problem number 1, 3 and 5 from your textbook. Let's solve 2 of them right now. Obviously first one is easy, I think, constant, but okay, Let's go to problem number 1. F of t. I write problem number f Laplace of f of t here, and remember this is a split function, I mean piecewise different function, and we have to write the integration for the first interval integral 0 to 1 e raised to minus st f of t. See, t less than 1, and of course our dimension starts from 0, so lower limit is 0, upper limit is 1, isn't it? F of t is minus 1 and dt, plus second part, t is greater than or equal to 1, so 1 to the upper limit is infinity, so infinity, positive infinity, e raised to minus st positive 1 dt. See, this negative 1 is from the first part, positive 1 is from the second part, right? Now integrate e power minus st. What do you get? You have seen integrations of different functions in calculus 1, 2, calculus 2 and 3, isn't it? So okay, so we will integrate e raised to minus st. You will get with respect to the variable t, so the constant is s, so negative s in the denominator, and the limit will be 0 to 1. Second part, again e raised to minus st will be on the numerator and divided by minus s from 1 to infinity. What's the next step? Next time I'm writing this side. This term will give you e raised to 1 over negative s is common, so apply upper limit for t, e raised to minus s, lower limit t is 0, e power 0 is 1 minus 1, and here again 1 over s is the second common term. S t is 1 e raised to minus s, and t e raised to minus infinity, e raised to minus infinity upper limit, which will be 0 minus e power minus s, power minus s. And now simplify this one. What do you get? Simplify. 1 by s in common, 1 by s in common, e raised to minus s minus 1 minus e raised to minus infinity will be 0 and minus e power s, isn't it? This is it. So you get 1 over s this will be positive 2 times e power minus s minus 1. That's the end of the first case, first problem. Let me solve you one more problem, 3. Problem number 3. Problem number 3. This one. So Laplace transform of the function f of t is equal to, first is interval 0 to 1, integral 0 to 1, function is e raised, the kernel is raised to minus st, function is t dt. The second part is integral 0 to 1 to positive infinity e raised to minus st positive 1 dt. Now integrate the first part by using integration by parts. Integration by parts, isn't it? That is known to you, and I am not elaborating it. So when you integrate by using integration by parts, you will find it t into e raised minus st divided by minus s. This is uv, isn't it? You can take u is equal to t, the rest is dv, isn't it? And then you can write integration by parts. Minus e raised to minus st divided by s square, so from 0 to 1 for the first integration. The second part is very easy, e raised to minus st divided by minus s from 1 to plus t infinity. And the first part will give you, when you substitute upper limit 1, get t is 1, e raised to minus s divided by minus s minus e raised to minus s divided by s square. This is for upper limit. Minus when s is 0, when t is 0, this term will be 0, this term will be 1. So 0 minus 1 over s square for the first term, isn't it? This term will become this term. Plus here, when you substitute upper limit, e power minus, it will be 0. Minus infinity will be 0. So 0 minus, and then t is 1, e raised to minus s divided by minus s. It will be positive. So the last what you get is here, this will be minus e raised to minus s over s. First term. Second term, minus e power minus s over s square plus 1 over s square. Finally, plus e power minus s over s. The first term and the last term can be cancelled. The rest is the answer. The answer is 1 by s square is common, so we can write common 1 minus e power minus s. This is the answer for second problem. Now, of course, I will solve problem number 5 as well. This one. Problem number 5, f of t is sin t in the interval. Second term is 0. So obviously only one part of the integration limit, Laplace of f of t is equal to integral. The limit is 0 to pi, and 0 to infinity actually the formula, but here it ends pi, and pi to infinity it will be 0. So this is e raised to minus st sin t dt, and the second integral will be 0 because the function is 0 here, right? Now we should recall a function formula. We should recall a formula for integrating this kind of functions. Integral e raised to ax sin bx. The formula is e raised to ax divided by a square plus b square into a times sin bx minus b times cosine bx. That's it. And then substitute upper and lower limit. This formula are going to be used here in this integration. Here remember what is a, the integration variable is t, so x is t here. The a is s, negative s. Oh, a is negative s and b is 1, the coefficient of t in sine. And b is 1 sine bx, x is t here, so b is 1. So let's use this one. E raised to minus ax, e raised to minus st divided by a square is s square plus 1 a minus s sin t minus b is 1 cosine t. Now use the upper and lower limits. This is the integration answer of this function. This is the formula for e raised to ax and sin bx. In the similar way, we have another formula for integral e raised to ax cosine bx dx. Here it is dx, which will be e raised to ax divided by a square plus b square, and here a cosine bx plus b sin bx. That's it. Okay, this one can be used if the function is cosine. Now the lower limit is 0, upper limit is pi. Substitute pi for t. So you get e raised to minus s pi divided Okay. A square plus 1, no, s will not be disturbed, only t, and here minus s sin pi, which is 0, sin pi will be 0, minus cosine pi will be negative 1, and next upper limit is done here, lower limit 0, 0. What happens when you substitute 0? E power 0 is 1 over s square plus 1, inside the bracket this will be 0, then 0 0 minus 1 minus 0 minus 1. So simplify, let's simplify this one, the next step, and then the answer comes. Then the answer is e raised to minus s pi over s square plus 1. Here sin pi will be 0, so the first term will be 0, minus of minus 1, and minus 1 over s square plus 1, and 0 minus 1. This is what we have to do. So we get here e raised to minus s pi divided by s square plus 1, the first term. The second term will be plus 1 over s square plus 1. That's the answer. The common denominator can be written s square plus 1 in the numerator, e raised to minus s pi plus 1. Here the condition is s is greater than 1. That's the end of all these 3 problems. Now we know how to use the basic formulas. Let's go backwards and check the slide. Basic results have been given here, isn't it? This is the Laplace transform of t power n, Laplace sin kt, Laplace sin hyperbolic kt, e raised to at, cosine kt. So some basic ideas should be recalled. I would like to recall these formulas in a different shade. Okay. My whiteboard, right? Okay, I would like to show you some basic derivations. Laplace transform of e raised to Laplace transform of t. Function is t now. The formula is 0 to infinity e raised to minus st t dt. Okay. We have to integrate this one by integration by parts. U is equal to t. I take v is equal to e raised to minus st. So u dash is 1, u double dash is 0. v1 integration of this one is e raised to minus st divided by minus s. v2 e raised to minus st divided by s square. So we have to use the formula here. What is integral uv dv is a different version of the integration by parts, which is uv1 minus u minus u dash v2 plus u double dash v3 is going on, isn't it? It will go on this way. U is t, v1 is given e raised to minus st divided by minus s, minus u prime is 1, v2 is e raised to minus st divided by s square. U double dash is 0 here after all the terms are zeros, so only 2 terms. 0 to infinity. So what happens when you substitute upper limit infinity? This is infinity and 0 indeterminate form. We'll get here e raised to minus infinity, so we'll leave this term. minus this time will be e raised to minus infinity is 0. For upper limit you will get nothing, isn't it? And lower limit minus t is 0, everything will be 0, minus t is 0 here, e raised to 0 is 1 over s square. So the answer is negative, negative, positive 1 over s square. Laplace of t power 1 is 1 over s square. And if you go this way, Laplace of t square, if you try in the same way, it will be 2 divided by s cube. You can try by using the same integration by parts. If I try Laplace of t cube, it will be 3 factorial, it will be 6 divided by s raised to 4. The degree will be 1 more than the degree of t. Degree of s will be 1 more than the degree of, so it is a t cube, then it will be s power 4. The numerator you will find this n factorial, this 3, if this is 3, then 3 factorial. If it is 2, 2 factorial, 2 factorial is 2, 3 factorial is 6, 4 factorial is 6 into 4, isn't it? 24. 5 factorial is 24 into 5, which is 120. In this way it's going, isn't it? So Laplace of, in general, you can find Laplace of t power n is n factorial divided by s to the power n plus 1. This is the first result in that table. Second is Laplace of sin kt and Laplace of cosine kt. How to find the rules for this one? By using the fundamental formula. We should take another important result, e raised to ikt. You remember e raised to ix is cosine x plus I sin x. There is a rule, if you don't know, remember, recall it. E raised to ix is cosine x plus I sin x in the complex field, right? So instead of x I take kt. E raised to ikt is cosine kt plus I sin kt. So if I find Laplace transform for the left hand side, I can separate the answer into two parts, real and imaginary, then find the result for Laplace of cosine and Laplace of sine, isn't it? So I'm finding Laplace of e raised to ikt. Use the same formula, integral 0 to infinity e raised to minus st. The function is written here, e raised to I kt dt. Now simplify the term, because both the terms are exponential, isn't it? So I can write integral 0 to infinity, t is the variable, isn't it? Integration variable, so you can write e raised to minus, you take out, say, so I will be, s will be positive, I will be negative, ik times d, isn't it? When you substitute it will be minus st here plus ik it will be, isn't it? Just the sum. When you integrate this one, there will be e raised to minus s minus ik times t divided by s minus ik. The upper and lower limits have to be used. The lower limit is 0, upper limit is infinity. Upper limit is infinity. So when you substitute upper limit, you will find e raised to minus t is infinity, minus infinity is 0. Lower limit will give you t is 0, 1, so 1 over this term. So what do you get when you substitute upper and lower limit? 0 minus 1 over s minus, what is it? S minus ik. Isn't it? Here actually there should be negative, because the coefficient is negative, s minus k, negative here, isn't it? So when you find the upper limit, so when you substitute upper limit t is infinity, it will be negative infinity 0, lower limit minus and minus, it will be positive. Here it will be negative, isn't it? So it will be positive finally. 1 over s minus ik. Since there is a complex number in the denominator, we have to take its conjugate and multiply s plus ik divided by s plus ik. Now the numerator becomes s plus ik divided by, this is a plus b, a minus b, s square minus ik whole square. I square will be negative 1 because I is in the complex field is square root of negative 1. So I square will be negative 1, so this will be positive. So answer is s plus ik over s square plus k square. So when you find Laplace transform of e raised to ikt, the answer is s plus ik divided by s square plus k square. Now let us write the into real and imaginary parts. So what happens? And if therefore the left hand e raised to Laplace transform of e raised to ikt can be written as cosine kt plus I times sine kt. The right side it will be s plus, so s plus ik divided by s square plus k square. So now let's separate, use linear property. This was the first term, Laplace of cosine kt plus I times Laplace of sine kt is equal to s over s square plus k square, s over this one plus I times k over s square plus k square. So this is real part and this is imaginary part on the left side. So this is real part, this is imaginary part on the right side. So comparing real parts, you will get Laplace of cosine kt is equal to s over s square plus k square. This is the result for Laplace of the cosine function. When you compare the imaginary parts, Laplace of sine kt, you will get k over s square plus k square. So k is the coefficient of this t in the function, remember. So when our cosine function comes, there is no constant in the numerator, only variable s comes in the numerator, right? But when there is a sine function, Laplace, if the sine function gives you constant the numerator and the s square plus k square in the denominator. This is the way to prove the rules. And of course there are some more rules dealing with it. For of course I will show you Laplace of cosine hyperbolic kt, Laplace of sine hyperbolic kt. So hyperbolic functions have relation with the exponential function. So we know the formula, cosine hyperbolic kt is e raised to kt plus e raised to negative kt over 2. Similarly, sine hyperbolic kt is equal to e raised to kt minus e raised to minus kt over 2. If you know these two rules, and if you know what is the Laplace transform of an exponential, that rule has to be derived first, isn't it? Okay, I will show you that rule as well. How to derive Laplace transform of an exponential function. Then everything is done in the first research, isn't it? What is Laplace transform of e raised to at? E raised to at. The formula is integral 0 to infinity e raised to minus st e raised to at dt. All are exponential, so e raised to minus s minus at dt from 0 to infinity. What do you get here? This what do you get here? E raised to minus s minus a times t divided by minus s minus a. So it is from 0 to infinity. Upper limit will give you 0, so lower limit 0 minus 1 over lower limit t is 0 will make numerator 1 over minus s minus c. The answer is 1 over s minus c. So this constant a will be subtracted from s, that is it. So if you know, then what is the Laplace transform of e raised to kt? Then it is 1 over s minus k. That is it. So when you use this result here, you can Laplace of e power kt, Laplace of cosine. If you take Laplace here, Laplace for every term, overall 1 by 2 is outside. Laplace transform satisfies linear property. That says you can find Laplace term by term. Constants can be kept outside. This constant multiplication can be kept outside. For example, remember this rule we will write here. What is Laplace transform of cosine hyperbolic kt? Right? This is the question. Now we will find Laplace transform of cosine hyperbolic is e power kt plus e power minus kt divided by 2. So linearity property says this constant is common, so 1 by 2 outside. First, Laplace transform of e raised to kt. Second, Laplace transform of e raised to negative kt. That's it. And we know Laplace transform of e power kt is 1 over s minus a. So Laplace transform of e power minus kt, when k is negative, it will be 1 over s plus k. Now this 2 is outside. What happens here? Take LCM. Then you may try to this s plus k plus s minus k divided by s plus k, s minus k square minus k square, 1 by 2 it outside, isn't it? So what do you get here? K will be cancelled, 2s will be there, and 2 will be cancelled. This 2 you get s over s square minus k square. So what we get? Laplace transform of cosine hyperbolic kt is s over s square minus k square. And you remember, if this is positive, the denominator, it will be not hyperbolic function on the left side, it is a be trigonometric function. For cosine kt, it will be s square plus k square in the denominator. But cosine hyperbolic function, it will be s square minus k square. The similar way, what is Laplace of sine hyperbolic kt? You remember what is Laplace of sine? It is k over s square plus k square, but it is hyperbolic, it is s square minus k square. These are the results given in this problem, in this PowerPoint. The results. Laplace sine k t, Laplace sine hyperbolic kt, sine hyperbolic kt, sine kt. All these results have been listed. Laplace transform of 1. It's very easy. You can prove 1 over c, because you can take Laplace transform of t power 0. Go ahead and just substitute t power 0 as 1 in the general formula. It is very easy to prove. So we have seen some basic rules here to derive the Laplace transform, and let's see to solve different functions as well. Now there are 3 different functions to find Laplace transform. Probably that will end this video. What is this? Hereafter we don't want to use this basics. Okay, you can use the basics, or no, we can. What is the question? Okay, we are supposed to use the basic definition, which is the integral formula, to find the Laplace transform of all these problems. So for these 3 problems also we should use the basic definition. Otherwise there are direct formulas we can use, but we are asked to use the basic formula, so we use that one. For example, problem number 11, Laplace of e raised to t plus 7 can be written as integrated 0 to cos t infinity e raised to minus st e raised to t e raised to 7. I separated e power t plus 7 to e power t power 7 ds dt, and e power 7 is constant, to keep it outside. Now club this one, integral 0 to cos t infinity e power e power minus, let's keep the minus outside, so this will be s minus 1 times t dt. Now integration will end and will give you this one, e raised to minus s minus 1 times t divided by minus s minus 1, and from 0 to infinity. So e raised to 7 the outside, inside it will be positive. When you substitute t is to infinity, it will be 0 minus, when t is 0, it will be 1 over negative s minus 1. The answer is e raised to 7 divided by s minus 1, and s should be greater than 1. That's the end. Problem number again exponential and t square you can try using. Okay, I'll show you one more problem, either 14 or 16. Okay, let me go with the 14. Problem number 14. Laplace transform of t square e raised to minus t. See, in coming chapters we have different method to solve these kind of problems, but in this chapter you are asked to use the basic definition of Laplace transform, so that's why we use the integration. This is integral 0 to infinity e raised to minus st is written every time. So second function is t square e raised to minus 2t dt. Now club the t's e power together, integral 0 to infinity, keep negative s negative outside, so e raised to minus t outside is s plus 2 times t and t square dt. Now again the integration by parts. I'm using the formula integral uv dv, which is u v1 minus u dash v2 plus u double dash v3. This formula is suitable when this choice of u is an algebraic function, right? Otherwise go with the original form of the parts, integration by parts. So it will go in this way, isn't it? So u is equal to 2t square, u prime is 2t, u double prime is 2, u triple prime is 0. So up to u double prime we have terms. There are other terms are 0. U double prime, u triple prime is 0, right? And what is v? V is e raised to minus s plus 2 times t. So v1, integration of this one is e raised to minus s plus 2 times t divided by minus s plus 2. v1, v2, v3. First v2 e raised to minus s plus 2 t divided by s plus 2 whole square, and v3 e raised to minus s plus 2 t divided by s minus s plus 2 whole cube. This information should be put in this order and then substitute upper and lower limit. You'll get the answer you want it. The answer is 2 over s plus 2 whole cube. I'll go for problem number 16. Problem number 16. Laplace transform of e power t cosine t. Integral 0 to infinity e raised to minus st and then this function e raised to t cosine t dt. We had to club the exponential together, 0 to infinity e raised to minus t outside, so this is s is positive, negative is s t, and this cosine t dt. Again remember the formula for integration of exponential and the cosine function. What is the formula? I'm writing the formula here. Integral So you remember this, I'm just writing the answer directly. E raised to minus s minus 1 times t divided by s minus 1 whole square plus 1 square and minus s minus 1 a cosine t plus b is 1 then sin t 0 for this entire term 0 to infinity. So here the formula is integral 0 to whatever the integration e power ax cosine bx, we have seen it, e power ax over a square plus b square a cosine bx plus b sin bx, isn't it? This one. And that's what here we are used to, and with the upper limit infinity and lower limit is 0. Now substitute upper and lower limits. You get infinity here, e power minus infinity will be 0. So first numerator upper limit will give everything 0. Lower limit is 0. E power t is 0, so it is 1. 1 over s minus 1 whole square plus 1 square. And t is 0, cosine 0 is 1, sin 0 is 0, second part is 0, so this is 1. Minus s minus 1. Therefore, minus and minus will be cancelled. S minus 1 divided by s minus 1 whole square plus 1 square is 1. That's the end of this problem. There are solutions in this slide. Now we are going to use the theorem 4.1. There are results. Laplace transform. What is Laplace transform of 1? Laplace transform of sin t, Laplace transform of cosine kt, Laplace transform of exponential at. All these results we have seen. We are going to use those results, isn't it, to solve this problem. 23. Problem number 23. Laplace transform of f of t. So let's take Laplace transform for term by term. Laplace transform of t square plus 6 times Laplace transform of t minus 3 times Laplace transform of 1. And remember, what is Laplace transform of 1? Which is 1 by s. What is Laplace transform of t power n? Which is n factorial divided by s power n plus 1. So t square 2 factorial is 2 divided by s3, s cube. 6 Laplace transform of t power 1, it's 1 over s minus 3 Laplace 1 over s square. Laplace transform of 1 will be 1 over 3 times 1 over s. So that's the answer. That's the answer. Problem number 29. Laplace transform of f of t is equal to, so first expand this one. Laplace transform of, expand the square. 1 square is 1 plus 2 times 1 into 2 times 1 into e raised to 2t plus e raised to 2t whole square is e raised to 4t. Now term by term. Laplace transform of 1 plus 2 times Laplace transform of e raised to 2t plus Laplace transform of e raised to 4t. And remember, what is the Laplace transform of e raised to 8t? It is 1 over s minus a. If this is negative, it will be positive here. Okay. So Laplace transform of 1 is 1 over s. This is 2. Laplace transform of e raised to 2t is 1 over s minus 2 plus e raised to 4t is 1 over s minus 4. That's the end of this problem. And this is straight away the answer from this previous one. You can choose from the results. Now this one, e raised to minus t into cosine hyperbole. We will solve 36. Problem number 36, e power minus t into cosine t. Let's write Laplace of e raised to minus t into cosine hyperbolic t can be written as Laplace times of e raised to minus t. Cosine hyperbolic t is e raised to t plus e raised to minus t divided by 2, isn't it? Now multiply this e power minus t inside. What do you get? 1 by 2 is constant, to keep the 1 by 2 outside as per the linearity property. And this e power minus t will be 1 plus e power minus 2t. This is what we get. So 1 by 2 is constant. The Laplace transform of 1 is 1 by s. Laplace transform of e power minus 2t is 1 over s plus 2. So that's the answer. That's the end of this problem. F of t is sine 2t. To solve problem number 37, you should have an idea about the basic trigonometric identities. You remember sine 2 theta is sine 2 times sine theta cosine theta, right? Theta is 2t. So you can write using this one, we can write Laplace of f of t, problem number 37, can be written as when you take theta, this will give you sine theta cosine theta is equal to sine 2 theta over 2. Take theta is equal to 2t. Theta is equal to 2t. Then what happens? This will be a Laplace of sine 4t divided by 2. So 1 by 2 is constant. What is the Laplace of sine 4t? K is 4. K is 4. The answer is 1 over 2. 1 over 2. The constant is 4 here. So you can write 4 into a square plus 4 square. And then 2 can be cancelled with the 4. You can write finally 2 over a square plus 16. That's the end of this problem. And problem number 40. We should have another identity. Cosine a minus b, which is cosine a cosine b plus cosine a cosine b plus sine a sine b, and here a is t, b is pi by 6 in the formula. So what will be Laplace of f of t? You can write Laplace of cosine a cosine t cosine pi by 6. Pi by 6 is constant. Cosine pi by 6 is constant. Plus sine t sine pi by 6. You get Laplace of cosine pi by 6 is root 3 by root 3. Cosine pi by 6 is root 3 by 2. Square root 3 over 2, and then cosine t plus sine pi by 6 is 1 by 2 and sine t. So in the first term, constant is root 3 over 2. What is Laplace of cosine t? It will be cosine t, cosine 1t, k is 1, 1 over a square plus k square is 1 square, isn't it? This is for the first term. Second term, 1 by 2 is constant. What is Laplace of sine t? It will be cosine. For cosine you will get s in the numerator. For sine you will get constant in the numerator. 1 over a square plus 1 square. That's the end. That's the end of this problem. Thank you very much. We'll see the next week chapters in the next video. Thank you.